My name is Denzil Ribeiro. I'm a principal product manager at Microsoft working on the Postgres service. And today I'm going to talk about 6 things you can do with the Azure AI and Azure Local AI extensions, which are first-party extensions. They greatly simplify building Gen AI applications on Postgres. So the first thing we'll look at is vectors and the importance of vectors in the AI era. Raw data such as video, text, and audio are passed to a deep learning model, which creates something called embeddings. And embeddings is nothing but an array of real numbers that represent the text or audio or video in a format that machine learning algorithms understand. And then using these vectors, then you can calculate distance. Distance between two vectors being close means they're similar to each other. And this vector similarity forms the basis of, semantic understanding tasks such as recommendation systems, query answering, and LLM retrieval. And they form the basis of also RAG or retrieval augmented generation. So RAG patterns with Azure Database for Postgres work like this. You have unstructured data, which is your text or audio or video, which is chunked and passed to an embedding model. And that embedding model, as we talked about in the prior slide, creates vectors which can then be stored in Postgres or Azure Database for Postgres. And then when a user asks a question, if the question doesn't have context and you go directly to an LLM, the LLM or the large language model has only public data, or is trained on public data. So it'll produce an answer such as, which is generic in nature. So if the question is, does my vision insurance cover LASIK? The answer would be more generic because it doesn't have information about domain-specific data, with regards to your insurance. However, if the question is augmented with context, aka you ground the LLM based on context of the data, so the question creates an embedding. The embedding is then searched within the database to get similarity results. In this case, it pulls out data to do with your insurance policy around your question and gives the most similar results to the prompts. And those prompts are passed to the language model. Then you'll get specific, answers. And, the question to the LLM is grounded on your data, and it then can figure out that, for example, your insurance covers LASIK with some stipulations. So Azure Database for PostgreSQL has native vector search via the pgvector extension. So you can enable the vector extension, and it allows you to durably store and index vectors and metadata at scale. So there are indexing strategies. We're not going to go into the details of that. You can index with IVF flat or HNSW and combine the vector queries. So this is not a specialized vector database. So your vector data resides along with your operational data. You can combine vector queries along with metadata search and then also enable ACLs on the vector data itself. So it's as simple as creating the vector extension and then inserting embeddings into a vector data type, which is a part of the table. So the Azure AI extension is a way for you to integrate, Postgres on Azure along with the AI ecosystem. So via SQL, so all the interfaces are SQL interfaces, which are user-defined functions, and they communicate with Azure OpenAI for embeddings, with Azure AI language service, which provides a host of language services such as sentiment analysis, summarization, key phrase extraction. You can do real-time translation via the AI translator, and then also invoke either custom-trained or pre-built models via Azure Machine Learning. And this is now generally available. We just announced GA a couple of weeks ago. So coming back to the 6 things we would do with the extensions, the first one is creating embeddings. And it simplifies creation of embeddings really a lot. The application, makes a call with a query to do a semantic search, for example. It's asking for high protein recipes. The database itself then talks to Azure OpenAI, passes the search string, which is high protein recipes, invokes the REST API call for Azure OpenAI, and then Azure OpenAI text embedding model returns a vector, which is the array of float data, and then performs the similarity search, which was the inner product comparing, similar to high protein recipes that exist on the database, and returns the result set. So without this, the application would actually have to talk to OpenAI itself, get the embedding, then pass the embedding in the SQL to the database and get the result set. So this simplifies that operation greatly. Remote embedding considerations. We support all the Azure AI embedding models, the text ADA 002 and 003. In text ADA 003, you have granularity, or you can specify the number of dimensions from 384 till around 3000 dimensions. And dimensions have a play in accuracy and recall. Just remember that Azure AI deployments have a token for tokens that you configure for deployment, and that controls the rate of requests it can receive. So you can specify as part of the call, timeout, retries, and delays in case you get rate limited based on the configuration of the deployment of Azure OpenAI. If you're not happy with the embedding models that exist on Azure AI, you can host custom, embedding models on the Azure ML integration piece that we'll look at a little later. And then this supports scalar or patch embedding generation. The second scenario we'll look at, which we've just announced in preview, is generating in-database embeddings without even having to go to Azure OpenAI. This is now in preview. So in this scenario, the application talks to the database, and the database hosts actually an Onyx runtime. The first model we have hosted is a multilingual E5 small model. This is an MS research model that is on Hugging Face. So, after the call for creation of embedding comes to the database doesn't even leave that machine, generates the embedding, and then returns that embedding to the application. So as I indicated, the multilingual E5 small is the model that is actually used as of now, and you don't have control of getting a custom model at this point. So why would you use in-database embeddings? The first reason is to reduce latency during embedding creation. Talking to an external service means there is a penalty for a round-trip latency of generating the embedding. The second is leveraging embedding models at a predictable cost, so you don't bank on multiple services. The billing is included in the billing for the database. And the third is to keep data within the database boundary itself. So if you have any requirements where you can't leave the database boundary, this is a way to use local embeddings. The simplified search experience is the same semantic search query looking for high protein recipes is passed to the database. It doesn't leave the database. That search string high protein recipes goes to the Onyx runtime, returns the vector. Similarity search is done within the database, and the results are returned to the application. So let's look at the demo of embeddings and the couple ways of doing embeddings. The first is with the Azure AI extension. I'm here in my Azure AI studio, and I am looking at deployments where I've deployed a text embedding 3 small model. The model name you can see there is the text embedding 3 small. And while configuring, I've configured a rate limit, which also limits kind of the requests per minute, right? So when you configure the deployment, that's what you configure. Now you have to allow list extensions in Azure before you can create extensions, and that shows you the extensions that are allow listed. This can be done from portal or API or CLI. The 2 extensions we are going to look at besides vector are the Azure AI and Azure Local AI. Azure Local AI is the new kid on the block that we've just previewed. We have a listings table. We are looking at Airbnb or vacation rental type scenario. So you have a listings table, which is a normal. And if I do a natural language like query, like looking at homes near Pacific Science Center that allow pets, with a traditional search mechanism like a like clause, returns no results. Similarly, full text search also isn't good for semantic search or similarity search. In this case, I added a TS vector query and did a text search. Still, I get no results. So let's look at creation of embedding. Before I generate embeddings, I'm showing the simplest form of creation of embedding. You call the Azure OpenAI create embedding UDF, and point it to a deployment in OpenAI, and then you pass it the search string, of course, the input, which is vector and embeddings power gen AI application. And there are parameters to ask for dimensions, which is text ADA003, and attempts and retry delay. So you can add now pretty easily embeddings to a table. For example, adding a column of vector type 384. In this case, I'm using 384 just because I'm going to compare with local embeddings. This is generated as always, so every insert actually generates the embedding. And then I pass the other parameters we've seen before. So if I look at the top 5 listings, I see the description vectors generated for all my listings. And now to search, to enhance my search speed, I create indexes, HNSW indexes in both cases. And the type of index creation depends on the similarity search you're going to do. In this case, cosine similarity and inner product. Now I can do my nearest neighbor or similarity search. And I've asked for 5 listings in this case with free parking and pets. You see free parking in this case in the title. And then if I flip to pulling the description, it's pulled out that it had a dog walking trail and dogs can come in. So it's deciphered that pets are welcome in the text. And the syntax is the order description vector has a cosine similarity search. Now, near Pacific Science Center might not actually mean much in terms of distance. It's relative. So I'm going to get the coordinates here for the Science Center. It's Seattle. And then use these coordinates to actually enhance my search. So in this query, I am doing 2 parts here. I'm going to search for vacation rentals within 2 miles of the Pacific Science Center because I have the coordinates, and add some additional metadata predicates. And then along with that, I'm going to do my similarity search, just like before, where I compare cosine similarity, the description vector, to my search string. And as a result, I get, a few hits, 4 or 5, places. I'm limiting to 5, within 2 miles of the location in interest. If I look at any one of them, you'll see that not only did it, get it within 2 miles, it also, deciphered that pets are welcome and parking is included in the most similar properties within my search parameters. So that is, we've looked at remote embeddings at this point and similarity search. The next thing we're going to look at is the same scenario with local embeddings. So I've made a copy of the table with listings local AI, and I've added already and pre-populated a description vector column, just like before. The only difference is these embeddings would be locally generated. The simplest form of generating the embeddings is calling the Azure Local AI Create Embeddings, UDF. And this time you pass the model URI and the input. It spits out the embedding based on this multilingual E5 small model. So similarly, I've updated the embeddings in this listing table because they take a little bit of time to generate. And the same similarity query as before now works. Now the results might be a little different because the model is different and your embeddings are different. So recall and accuracy between models plays a role here, but it returns results that satisfy the criteria. per the model. And if we look at performance now, I'm going to generate embeddings, 100 embeddings just for good measure with the local UDF. So these are generated in database. And I do an explain analyze and see that these 100 embeddings took about 1.3 seconds, which is pretty good from an average perspective. If I look at remote calls for kind of the same scenario, 100 embeddings, calling the Azure OpenAI create embeddings call, you see the same 100 embeddings took 6.2 seconds. So that shows you the difference in speed between local embeddings and remote embeddings. So to show that further, I have just wrapped those embedding calls within UDF. So get remote embeddings gets it from an OpenAI deployment, and get local embeddings gets it from the database. And I'm running pgbench in both cases. You'll see a difference in TPS on the left and on the right. This is just one client. The TPS is around 242, and the average latency is 4 milliseconds versus the TPS on the left at around average latency is 61 milliseconds, and the TPS of around 17 embedding generations per second. So that's embeddings in a nutshell. The next thing we're going to look at is some of the language services. We'll start with sentiment analysis. These are machine learning models using NLP techniques that detect the language. Language detection is at the forefront or key ingredient of any of these language services, and they provide sentiment labels. So they classify, for example, a review as negative, neutral, or positive, and provide a score for each of those. And they support like over 100 languages or around 100 languages. So the sentiment analysis can do sentiment analysis on about 100 languages. And that's done via the Azure AI extension. And I'm going to club a couple of these before we go into the next demo. The next one is summarization and phrase extraction. These are used to, if you've seen Amazon, you've seen the AI-generated summary of reviews, for example, or can be done to summarize legal documents. There are abstractive and extractive summarizations. One extracts points within the document. The other actually summarizes the document. And again, these have multi-language support. And the next fifth thing we'll look at is real-time text translation. In real-time text translation, again, we detect the language automatically. We are able to translate in 100 plus languages, and we are able to transliterate, which means it's more of conversion of characters into the different language rather than literal translation of sentences. And then there's other functionality such as filtering out profanities and the like. So let's look at a demo of Azure AI language services and translation at play. So here, the first underpinning of language services is language detection. So Azure Cognitive is the schema here, and detect language detects language of any text, and it's implicit in most cases. You don't have to actually do a detect language. So I have a reviews table for my vacation rental, and detecting sentiment is as simple as calling a UDF, Azure Cognitive.analyze sentiment, and then out comes a sentiment text, positive, negative, or neutral, and a score for each of those components. So you can do things like take all your reviews and average them out. For my top listing, for example, which is listing ID listed there, I can actually do an average score. It seems like it's a pretty good listing with 34 positive reviews and 1 negative review. Or I can combine some of these functions. In this case, I'm combining a summarize abstractive along with all my reviews. So I take all my 34 reviews and pass it to summarize abstractive. I aggregate or do a string ag on all my reviews so that I combine that to form a document. But you could summarize a document as well. And I get a summarization of that review. So in this case, you'll see I copied this out. You see the reviews generally positive. So the overall summary is positive. Um, you know, in addition, we have other functionalities such as key phrase extraction. If you want to highlight the phrases within a document or a review or a listing, in this case, there are the key phrases that you could highlight. And last but not the least, I snuck in another one, which is PII redaction. PII redaction actually identifies what elements of a string have PII. So things like a name, an address, an email address, a company name, and then they'll mask that out and give you the classification and the confidence of that classification that you can actually get for the redaction. So these are language services in a nutshell. Then we'll look at translation. Translation in real time also is very easy. We have the translate API, and in its simplest form, you pass a string and a language, and you get the translation, right? You can also do this in multiple languages at a time by passing an array of languages. Here, you got the same string into multiple languages. And then there are things that you can do around, profanity filtering, for example, where you can either delete profanities or mark profanities or put a placeholder for profanities. So in some languages, and it is language sensitive. So idiot, for example, is not necessarily masked out in certain languages. So you can use the same thing to translate reviews, for example, in the locale of a user. If you have an international audience, for example, here's my listing in question, and I've translated all these into Portuguese. And then all these UDFs, for ease of use, could be wrapped in a function to simplify, calling into them even more. So in this case, I'm getting translated reviews in French, and the top 5, right? The last area we're going to look at is real-time predictions with Azure Machine Learning. So Azure Machine Learning has a robust platform and can expose real-time endpoints. And those endpoints you can use for real-time scoring or predictions. They have inbuilt features like you can define the cluster size, there's auto scale, you can enable traffic routing if you have multiple models, and you can host a variety of models. You can train your custom models that you want, or you can host pre-trained models from a catalog of models. If you're not happy, for example, with the embedding models that we talked about already, which are the ADA 002 or 003 or the inbuilt in database one, you can host a custom embedding model as well. So the last demo we'll look at is the Azure ML integration. Here I have Azure AI Studio. And in my Azure AI Studio, I have the online inference endpoints. Here I have an online inference endpoint that is hosting a few models here. The one we'll look at specifically is the California housing, but I also have a pre-trained model, which is the Phi2. The first thing you do is once you deploy the model, and we're not going to go through the training exercise, is to test the model within this interface as well. Because if it doesn't work here, it's not going to work within the UDF calling it. So here I've passed, 2 arrays of data, which are 2 sets of features, and I got 2 predictions. And to configure, you would configure the endpoint for this within the extension, which that then uses it to call into that. So here I have a table which has my features that the model require. So this is a house prediction model. So as you can expect, the features include things like average rooms, age of house, population, and so on and so forth. And the output is the house value in hundreds of thousands. So in simplest form, you invoke with a JSON parameter, pass the input data that the model expects, and call the Azure ML.invoke, passing with the deployment name in question, and then pass the input data that the model expects. Here I'm passing 2 sets of features. Similarly, you can build that JSON input for a specific property. Here I'm building the array for the features and building the JSON object itself. And then once I have those two, I invoke the Azure ML.invoke for that deployment in question. And then you'll get the price prediction for that one listing, which has ID 18,000. And that's the price prediction. So the easiest way to do this, both to figure out the resources it takes and the number of times it's invoked, is to create a function, because you can then see usage of that function. Has the same logic, and we invoke it with the listing ID. Here it converts it into a real. If we validate a model, it was 2.7 million. It's 2.7. The actual was 2.773 million. Our model is pretty good. So I'm showing you a pre-trained model here, which is the 5.3 model. It's not something you would actually use within a database, but want to show that you can include pre-trained models here. So this is a text generation model. I ask it the question. It's an LLM. I ask it what's the most loved Postgres function or feature, and it replies with it's the supported for advanced data types and functions which allow complex and efficient data manipulation. So this is an LLM grounded on public data set, of course. So we've seen several things now. We've seen the Azure AI extension, the Azure Local AI extension. We've seen embeddings, similarity searches. We've seen Azure ML integration and a host of language services. All these greatly simplify building Gen AI applications on Azure Database for Postgres. Here are some resources that have documentation and other links to learn more about the feature. I appreciate your time. Thank you for listening. And we are eager to hear about all the awesome things you build with the Azure AI extension.